Hello students, welcome to the 7th video on the series Microwave Layout Analysis. This is the microwave layout for 1-bit SRAM using NMOS switch. As we see here, we are having the write line and we are having the read line. And between the write line and read line, we are having the NMOS N1, NMOS N2. We have the CMOS inverter I1 and CMOS inverter I2. Inverter I1 and I2 are connected in a cross-coupled fashion. That is, output of inverter I1 is given as an input to the inverter I2 and the output of inverter I2 is given as an input to inverter I1. This is the enable signal which will decide whether the NMOS switches N1 and N2 will remain on or off. So basically 1-bit SRAM cell is a combination of two NMOS switches N1, N2 and two cross-coupled inverters I1 and I2. As we see here, the enable signal is equal to 1. This 1 is applied to the gate of NMOS N1 as well as to the gate of NMOS N2. N1 and N2 being active high devices, N1 will be turned on and N2 will also be turned on. Now let us consider the first case where the write line is connected to 0 as indicated by write minus. So we have a 0 written here. So 0 is applied to the drain of N1 and N1 or NMOS transmits 0 as strong 0. This strong 0 is applied to the inverter I1 which will convert strong 0 into a strong 1. Strong 1 is again applied as an input to the inverter I2 which will convert strong 1 into strong 0. Now as we can see here that the second NMOS N2 is getting a strong 1 here through this path and as we know that NMOS is not good at transmitting ones, so when strong 1 is applied to the drain of N2, it transmits a strong 1 as a weak 1. Therefore, for enable equal to 1, write equal to 0, we get read equal to weak 1, which is not acceptable. Let us now analyze for write equal to 1. Erasing all previous values. write line is connected to logic 1. The drain of N1 receives a 1. NMOS transmits 1 as weak 1. Weak 1 is applied to the input of inverter I1. It converts weak 1 into a strong 0. Strong 0 gets applied to the input of inverter I2 and it converts it into a strong 1. Strong 0, that is output of I1, is transmitted. Strong 0, the output of I1 is transmitted through this line to the NMOS device N2. So we have a strong 0 here, and because NMOS is good at transmitting zeros, we get read equal to strong 0. So for WR equal to 1, we have read equal to strong 0, which is acceptable. So we can summarize the analysis. Oh yes, we forgot to analyze it for enable equal to 0. For enable equal to 0, 0 is applied to the gate of NMOS N1 and to the gate of NMOS N2. NMOS being an active high device with gate at logic 0, N1 is off and N2 is also off. That means the logic written on the right line, the logic written on the right line will not reach the cross coupled inverters I1 and I2. So irrespective of the value of right, whether it is 0 or 1, the right line remains disconnected from the read line, even though a CMOS inverter is an always on system. So for enable equal to 0, right is don't care and read exhibits a no change. Let us see what the simulation says. For enable equal to 1 and right equal to 0, so we see here for enable equal to 1, right equal to 0, we get read equal to weak 1. We will remove the visibility of NMOS input. So enable equal to 1, right equal to logic 0, read equal to weak 1. How do we conclude it is weak 1? Because the output is not attaining a value equal to 1.2 volts, which is the VDD for 90 nanometer technology. rather it is settling at 0.90 volts. The difference between 1.2 and zero point 0.9 is nothing but the threshold voltage of an NMOS device. For write equal to 1, we see here when write is equal to logic 1, read line is resting at 0.0 volts minus VSS, that is a strong 0. Let us see what is the value, what is the output for enable equal to 0. For enable equal to 0 and write equal to 1, the output is at this level, it is almost 0 volts. Let us change the write to logic 0 and see if there is a change in the value of read. For enable equal to 0, write equal to 0, we see that there is no change in the value of the read line. Thank you very much.